definition of heat capacity. Someone can just shout it out for me. What letter is it given by? Capital C, love it. Okay. Just read it from your notes for Monday. Somebody has to have it at their ready. Thank you, Paul. The amount of heat required to raise the temp of some amount of substance by 1 degree Kelvin. Okay, so I'm going to write that down again. Amount of heat required to raise the temp by 1 degree Kelvin. Is it an extensive property? Yes, it depends on how much of something you have. It takes more heat to raise 2 grams of water by 1 degree than 1 gram of water by 1 degree. Okay? And so we said the units for heat capacity were going to be joules per Kelvin. Sometimes you might see them as joules per mole Kelvin. Okay? And that'll be heat capacity for 1 mole of whatever we're interested in. Okay? But sometimes when you see per mole in the bottom of something, it's a clue we're talking about an extensive property. So we can think of C as change in energy over change in temp. And we can also write it as dq, change in heat, over dt, change in temp. And we can rearrange this as heat is equal to heat capacity times change in temperature. And heat capacity comes in sort of 2 flavors for us. Okay, so we're going to have for constant volume, and we're going to call this isometric heat capacity or constant volume heat capacity, C sub V. Okay. And then we'll also have for the constant pressure case. And that's C sub V. Okay. So right now we're talking about ideal gases still. So for the constant volume case, remember that we have our first law of thermo, du equals dq plus dw. dw drops out because there's no work done. Okay, so we have 0. So then what we can rewrite, since du is equal to dq, we can plug du into the equation that we have above. So C sub V would be equal to du dt. Okay, instead of dq dt, du dt. For an ideal gas, we said that U is equal to 3/2 number of moles times the gas constant times the temperature. Okay. And again, this comes from the fact that we only have kinetic energy. Okay. All right, du is equal to 3/2 nr. These are all constants, dt. Okay, so then plug this piece in to the equation above. Our constant volume, or our isometric heat capacity, is equal to 3/2 nr dt over dt. So this is going to drop out, and we have 3/2 nr. It's a constant, but it depends on number of moles of gas you're talking about. Okay? But our heat capacity for an ideal gas is a constant. So we can go back up to this equation and write dq is equal to isometric heat capacity times change in temperature. And we can integrate this to get total heat. So we're going to have q is equal to the integral from T1 to T2 of, yes I can, there we go, CV dt. Okay. This would be equal to isometric heat capacity times T2 minus T1. So you might see this as 3/2 nr T2 minus T1, 3/2 nr delta T. And those are all variations on that equation that you might see. And so then next we'll talk about the constant pressure situation. So when we think about a constant pressure process, we have a couple, first of all, we're only ever interested in enthalpy when we're talking about constant pressure. This is our definition of enthalpy in terms of all its state variables. Ideal gas law, PV equals nRT. So first thing we want to do is plug this in for our PV term in enthalpy. So we have enthalpy is equal to internal energy plus number of moles of gas times gas constant times temp. We write it as change in enthalpy, so we'll have dH equals du plus nr, our constants, dt. Divide everything by dt. Okay. So we have dH dt, du dt, and dt in this part drops out. Now we also said that dH is equal to constant pressure heat. This term here is this term here. So we can plug in our isometric heat capacity for the du dt term. And dH dt is the definition of our constant pressure heat capacity. Okay. C is equal to dq dt, but dH is equal to change in heat at constant pressure. So we can rewrite this as we can plug this in for this piece here. And we can say that constant pressure heat capacity is given by dH dt. And plug this piece in here now. So what we have is constant pressure heat capacity is equal to isometric heat capacity plus nr. Okay. Du dt was Cv, dH dt is Cp. This dropped out, we have nr left. So this is equal to 3/2 nr, our constant, plus moles times gas constant. This is equal to 5/2, and 1 is 2/2, 5/2 nr. Also a constant. The constant pressure heat capacity for an ideal gas is higher than constant volume heat capacity. Does that make sense? And why?